Hi friends, this is the second part of my series on time evolution in Qiskit. Okay, in the last video I made a brief recap of time evolution in quantum mechanics, and I showed you simple ways to implement time evolution using Qiskit. Okay, and in this video I'm planning to show you how to get the state vector of a quantum circuit involving no measurements. Okay, in the case where the circuit involves measurements of classical bits, if you wish, things get a little bit more complicated because you need to use simulators in Qiskit. So I'm gonna prosecute that to another video, and in a further video of the series, I'm gonna show you how to get expectation values using the state vector of your quantum circuits. Again, maybe you're a physicist interested in getting no information about your quantum circuit and calculating, for example, expectation values and so on, and all such functions are the functions such function of that I'm showing you are the functions I found easier to work with. Okay, in my opinion, to get the state vector of a quantum circuit, it's easier to use this state vector class from Qiskit.quantuminfo library. Okay, it's very straightforward, as I'm going to show you in this simple code snippet. First here, I'm importing the quantum circuit function from Qiskit library, and then I'm importing this state vector class or function, if you wish, from the Qiskit quantum info library, and defining naturally a 2-qubit quantum circuit, for example. Okay, then let us apply, in order to the state of the circuit not to be trivial, let us apply some gates before getting the state vector. So I'm applying here a header mark in qubit 0 and a CX with qubit 0 as control and qubit 1 as target, and another header mark in qubit 1. If you're not familiar with that, I recommend you to search a little bit about the standard gates of Qiskit. Okay, and then I get the state vector of the circuit, this little circuit here, very easily. I simply define psi, this variable here, as state vector and pass QC as an argument of this function. Okay, we can make, Qiskit also allows to make a drawing of the circuit, which in LaTeX, of course, which is a very nice feature. If you wish to confirm your results, you can check out, think a little bit using the definition of the Hadamard and the CX gate. You can check out that the state of the circuit is indeed this one. Okay, hopefully this is clear, and this is all to get the state vector of the circuit. I'm going to show you actually in this video more examples involving the circuits I've considered in my last video, but mainly the explanation of how to use the state vector class is simply that. There's no mystery. Okay, looking at more examples, in the last video I considered here a quantum circuit of a single qubit involving only one qubit state of the harmonic oscillator. So I defined these operators here, A and A dagger, in terms of the Pauli gates, and then I constructed the Hamiltonian of the harmonic oscillator and a time evolution operator, and applied this operator to a circuit involving, of course, one qubit only, using this unitary function. Okay, here's a drawing of the circuit. This was considered in the last video. But if I wish to get the state vector of the circuit, I can use, as before, the state vector class, and I define here my state vector as psi underline QC. This time I plotted it here in LaTeX. Of course, because the state 0 is a stationary state of the harmonic oscillator, the name already suggests, after I apply this unitary time evolution, I get nothing interesting because it's a stationary state, of course. And if I wish to consider, for example, something more interesting, I can apply, before making the time evolution, I can apply, for example, a Hadamard gate here. Okay, in this code snippet, I'm not considering actually the time evolution, just for you to see that the state produced by the Hadamard gate is this equal superposition, like as expected. But if I put a unitary time evolution here between the defining of the circuit and the getting of the state vector, I see that indeed I get something different from the last state before the time evolution. Okay, I'm setting here this parameter omega t of the unitary time evolution as in at pi over 2. So this picture here can be more beautiful if you wish. But if you wish something even more interesting, you can set that equals to pi over 4, okay? And then you get this crazy state vector here, and then you can play around with such things in order to get a better understanding. I consider also in the last video this 2 qubits quantum circuit, okay, involving 2 qubits of the harmonic oscillator. This first part of the code is the same as before, but here I defined the composite Hamiltonian as a tensor product of 2 Hamiltonians of single qubit states of the harmonic oscillator, and then I applied this to this quantum circuit using the same unitary functions, but modifying here this argument qubits. I recommend you to check in the last video. But I can play around and go even further by defining a 3 qubit quantum circuit, okay, making a triple tensor product here, and evolving this quantum circuit and get its state vector. Okay, I applied first these 2 Hadamards here in this part of the code in order to these states not to have a trivial time evolution, and then I applied the time evolution operator and got this state vector here. I recommend you again to think about it using the definitions from usual from basics of Qiskit and quantum mechanics. I hope that it's clear how to get the state vector of a quantum circuit, and in the next videos, as I said earlier, we're gonna check out how to get the state of circuits involving measurements, and then how to get expectation values using the state vector from quantum info library. Okay, so hope to see you in the next video, and goodbye.